Hello, and welcome to this webinar, where today we are going to be talking about optimizing and accelerating your MATLAB code. We're going to look at a variety of examples and techniques for improving the performance of your algorithms and applications. Let's take a look at the agenda. We're going to begin by looking at ways we can optimize for loops within MATLAB and take some advantage of some of the native features of the MATLAB language, like vectorization. Then we'll look at how we can spend our time efficiently by addressing the proper bottlenecks in the code. We'll look at how we can incorporate compiled languages like C and generate C code from our MATLAB code. Then we'll switch gears and look at just using more hardware, so parallel computing, GPUs, clusters. And then summarize at the end what we've gone over and a few additional resources. Our very first example, we're going to jump right into it, is going to be to calculate an image, build an image, and then take the mean of a bunch of blocks in that image. Let's just jump right into MATLAB. So our goal for this example is we want to take block average, the function you see on the side here, and right now I'm calling it, I'm going to build a 3000 by 3000 image and then take the mean of every 25 by 25 block. You can see it's taking a little while. And my goal is that I'd like to get this computation time down. Took about 16 seconds. And after a few redos, we'd like to see it a little bit faster. So let's get started. So block average is a function. It takes inputs. You might notice that I've started off with an if here. These are it's just assigning default. So if I didn't provide the 3000, 3000, it would assume 1500 by default. We're going to start a timer with the tick command. Tick starts a timer, and then you can use the talk command to see the elapsed time. Then we're going to do a for loop over some grid points, calculate a function. This is that function for that wavy equation you saw in the image. And then we'll do a couple more for loops to calculate the mean of each block. And then we'll talk it at the end and plot. So what's the first thing you might notice about this? Well, oftentimes people will say there's two for loops, which in itself is not inherently a bad thing. You might also notice an orange underline here. This is the MATLAB Code Analyzer. The MATLAB Code Analyzer is a little MATLAB expert sitting on your shoulder, pointing and saying, hey, I think this is something you might be able to do better. It'll tell you about possible performance issues, possible bugs. It's a very nice thing to listen to. So we can see in this case it says, the variable mysurf appears to change size on every loop iteration. Consider preallocating for speed. And if we look, this actually occurs in a bunch of different places. If you use MATLAB a bit, you might recognize this message. It's probably the individual biggest time consumer in MATLAB. So let's demystify it a little bit and explain what we mean by preallocating. So right now, with these for loops, on each iteration, we're going to the operating system and saying, hey, we need space for some amount of data. So for example, we say x of 1 equals 4. We'll ask the operating system for a 4. Hopefully it gives us the space. When we say x of 2 equals 7, the operating system needs to allocate space for two elements, copy the 4 over, insert the 7, clear out the old value. If I was to then say x of 3 equals 12, it needs to copy the 4 and the 7, insert the 12, and clear out the old 4 and 7. So for a little 3x1 example like this, that's no big deal. But I'm doing this on a matrix that's 3,000 by 3,000 elements, which means that on the 2,999th iteration, it's copying a 2,999 by 3,000 array. And this starts to take a lot of time. So what we can do instead is say we know ahead of time how big the matrix needs to be. So we'll reserve space with zeros for that. And then as we insert the values, we're not having to do a memory copy on each iteration. And these reduced memory copies will speed up the application. I have my first redo right here. I'll do a code comparison. We can see on the left I have the original block average command, and on the right I have block average redo 1. And the only differences are that I'm reserving zeros to be the final size of the array. So let's run this block average redo 1, and it was 3,000. And we can see that we've already shaved off almost 10 times the amount of time required. It went from about 16 seconds down to 1.9 seconds. So for loops in MATLAB aren't necessarily a bad thing. For loops are actually really fast, but there are things that we can do to make sure that they are running at their finest, like preallocating. A few other things that we could do are make sure that we are avoiding repeat computations. So like right now in this example, I calculate 2 pi, 2 pi, 2 pi on each iteration of this loop. So I'm calculating it 27 million times. 2 pi hasn't changed a lot in the last few thousand years, so maybe I should pull that computation out to save time. So we saw the original example. I got it down to be even faster. Let's pull up block average redo 2 and take a look at it. So here you might notice that there are no for loops. So what I'm doing is building a grid of values. In a grid, here's a simple example of a grid. So now I have a grid of values, xx and yy. Every column of xx is the value of that column, and yy is the value of the row. And we can, because MATLAB actually stands for Matrix Laboratory, we can work on xx and yy directly. So I could add xx plus yy times xx. And now, rather than using the loops to loop over every element, I'm applying that operation to the entire grid at once. So if we look here, I've built the grid, and now I'm going to evaluate the MySurf equation or formula on the entire grid at once. Well, how are we going to calculate the mean of each of those blocks? Earlier, you could picture a sliding window scanning over the different pieces. But now, you'll see a bunch of reshapes, transposes. So this is what we call vectorizing an operation. We're working on the entire array at once. In this case, we're reshaping it into the third dimension so that we can take the sum along specific dimensions at a time and eventually yield our mean. And what this will allow us to do is to squeak out a little bit more performance like you saw at the very beginning. So even for people who use MATLAB all the time, vectorizing code like this can take a little while. So it's important to consider the entire lifetime of the code. If this is something we just need to run a few times, it probably makes sense to just stick with the for loops. If this is something we need to run 1,000,000 times, it's probably worth rewriting it with this technique in order to squeak out a little bit more performance. Now, if you're looking for general techniques on how to vectorize your code, there is a documentation page that goes over a bunch of the common techniques for vectorizing code. So this is the MATLAB documentation, and it provides examples and common operations that you might need to do. At the bottom, it also provides a list of functions that you'll use often, so you might recognize here the reshape that we were just using. Our next example is going to be on indexing. So if I have, let me just create a small example matrix here, a little 5x5 magic square. If I want to extract this element from X, I could ask for x of 2 comma 4. And that would give me the second row, fourth column. I could also ask for x of 17. So this is the 17th element in the array. MATLAB stores arrays column-wise. So 17th element. Oftentimes, if you don't need both the row and column coordinates, you can use linear indexing, like this x of 17, to index into an array faster. And there are conversion functions sub to int and int to sub to go back and forth. Alternatively, if we needed to get the value 14 out of this matrix, I could ask for x of x equal to 14. And this would return the 14. So this is logical indexing. And what's happening is under the hood, MATLAB is building a logical or binary matrix that it can use directly as an index. And this can often be the fastest form of indexing because you don't need to know explicitly where the 14 is. You can just grab it out or do some operation on it. In terms of performance, I'm going to do a small example where I do the equivalent of this on a much bigger matrix. So I'm going to grab all of the variables in x that are greater than 20, or all the values in x that are greater than 20. Except now I'm going to do it with a much bigger matrix. So I'm going to do it with a 4,000 by 4,000 matrix, and I'm going to grab everywhere that's greater than 1,000,000. And we're going to look at a few different techniques for doing this. I'm first going to use a double for loop. I'm going to loop over all the values in this matrix. On each iteration, I'm going to extract the value if it's greater than the threshold. Then I'm going to use the find command to do this. You might actually notice find is saying, the code analyzer is saying, Sean, you might not need this find because you could use logical indexing instead. Find would return the linear index. And then I'm going to use logical indexing directly. And so when I run this, you can see the two for loops are actually pretty fast. We're doing 16 million iterations, and on each iteration a check on the threshold in about half a second. And then find costs a little bit more overhead than just doing the logical indexing directly. So what's going on under the hood here? Starting in MATLAB R2015B, there's a new execution engine for the MATLAB language. When you run it, all MATLAB code is just-in-time compiled. And we say that this improves the nth run performance. So on the first time you run something, you might notice it being a little bit slower than the subsequent time. And that's because the first time through, it's doing this just-in-time compilation, and on the second pass, it can use those compiled instructions from the first run. Also under the hood, MATLAB uses a bunch of commercially available libraries that are highly optimized and multi-threaded. These are a few of them. So if you're doing things like linear algebra, we're already using highly optimized libraries for it. And this is one of the reasons that you can see some speed up with vectorized techniques, because we can piggyback on these libraries. So what are some other best practices? Well, because of this just-in-time compilation, you want to avoid the command clear all, which will clear out any of the just-in-time compilation that's happened. If you need to clear your variables, just use clear or clear-vars. Clear all is a big hammer approach. Functions tend to be faster than scripts because they have a static workspace. So if you're really looking to optimize a piece of code, consider turning it into a function. As files get large, the execution engine has to build the entire branching structure for all possible branches through it. Because of this, smaller files tend to be faster. Also, avoid introspection functions like dbstack or input name, things that have to query the state. For more techniques on improving performance, also look at the MATLAB documentation. So now we've looked at how to use the MATLAB language more efficiently. But how about how to use our time more efficiently so that we're focusing on the proper bottlenecks and not something that just takes less than 1% of total runtime? So for this example, we're going to run-in time of program, we're going to identify the bottlenecks and then try to correct some of those bottlenecks. The specific example we're going to be using is we're going to load data from a bunch of files, fit a spline to it, write the results to Excel. So my goal for this is I want to take the equivalent of this test fit. Right now, you can see it's looping over about 10 files. And I want to do a few redos to get it to run like this. So a bit faster. So we can see right now that the green box in the upper right-hand corner of the function is, that the box is green in the upper right-hand corner of the function, meaning the code analyzer doesn't have anything to tell me. You might see on the editor tab here this run in time button. And so what this will do is it'll use the MATLAB profiler to run our function. It's going to time each function call, and it's going to tell us how many times each function was called. So if we look at test fit, we can see that it was called once. You can see that write table was called 10 times and individually took the most amount of time. In fact, all of these next few pieces are part of write table, where we're writing our variable to the Excel sheet. So if we look at the code right now, you can see that we have this for loop. It's looping over the number of files that we have. So it looks like we have 10 files. And on each iteration, calling write table, which is writing it to this custom range in the Excel sheet. The for loop then ends here. So right now what's happening is 10 times we're doing essentially the same thing as you clicking the Excel icon, opening Excel, writing a bunch of data to it, saving it, and closing Excel. So might it be more efficient to just do all of the writing once at the end? So that's what our first redo is. Rather than writing everything on each run, I'm going to preallocate a table. A table is a container for holding heterogeneous column data, like spreadsheet-like data. On each iteration, we're now just going to update the variables in the table with our new data. So we're going to update the corresponding columns. The for loop ends on this line, and we're going to call write table once afterwards. So now we'll run in time test fit redo 1. So you can see it's a little bit faster. We can see that the dark band here, the self time in test fit redo 1 is larger, which means that more of the time is being spent inside of this function rather than in functions it calls. So let's step into test fit redo 1 and see what's happening. Now we get a breakdown of the top offenders within test fit redo 1, and we can see that text scan is called 590 times. Jump down to the line. The entire function is here below with red highlighting indicating the amount of time taken per line. And we can see that apparently this text scan is inside of a loop that's running 59 times. So let's just jump to that line and see what's going on. So this loop's running from 1 to desired test minus 1. I don't know how many of you have used text scan before, but one thing to check with most of the functions you use is that they often have flexible calling syntaxes. So if I open up the documentation for text scan, we can see that there are a bunch of different ways that I can call it. Different format specifiers, I can use n, and we can see a description of what each of these is. And so right now, n is the number of times to repeat this format specifier. What I'm doing here is looping over rather than unrolling that for loop into the text scan call. If we look at my next redo, we can see that I've unrolled the for loop into n times the desired test minus 1. Now, I know most of you aren't using TextScan every day, but this is just a hint that sometimes functions have different syntaxes that can be more efficient. So now we'll run in time test fit redo 2. See that we're down to about half of our original execution time. Jump into test fit redo 2, see what's going on. Now we can see draw now is the top offender. It's called 10 times. Write table, there's probably not much we're going to do to make write table much faster at this point. It's a necessary evil. And then we have some graphics things, close all, figure. Well, draw now is actually also a graphics call. What's happening is on each iteration, we're plotting the current iteration of the data, and then draw now is forcing the graphics to update so that we can see it on the screen. And we would have to do this if I was uncommenting this line here that's actually saving these files off. So the draw now is a necessary evil if we need to have the graphics updated. But you might also notice that figure and close all are both taking some time. So right now on each iteration, we're spooling up a new figure, and then at the end we have to close all 10 of those figures. So if we were just saving off the figures at the end, it might make more sense to reuse the same figure over and over again. So if we look at this now, the only difference between these two files for this third redo is that the third redo does not create new figures. And if we run in time the third redo, you can see that it's a lot faster. We're down to 1.2 seconds, or we've gone about a 5 times speed up by doing this exercise. So what does the profiler give us? It gives us total number of function calls, the amount of time those function calls took, where this time is spent, whether it's in a function or a function that function calls. It also gives us code coverage to see if all of the code ran. So what are some good best practices here? First, we want to minimize file I/O. It's much faster to have data in RAM than it is to read it from disk. Try to reuse graphics components if you can, rather than overwriting ones, or rather than clearing or overwriting ones that exist. Modify them. And also, if you've ever left the semicolon off a large array, you might notice that it takes a little while. Printing to the command window isn't the fastest thing in the world, so it's okay for prototyping, but when you actually move something into production, or when you need to have it run really quickly, it pays to not print to the command line. So what have we done so far? Well, first, we got our code working. This is important. We don't want to prematurely optimize, spend a bunch of time trying to get code to be really efficient, but have it not give us the correct results. So first get it working, then start looking at speeding it up within MATLAB using things like the profiler and some of the core features of the MATLAB language. If you've already done this and you're still not getting the performance that you need, that's when it's time to start thinking about using compiled languages like C or Fortran for some of the very specific bottlenecks, and we'll talk about what those could be, or additional hardware. So with that, let's look at generating C code and incorporating it within our application. Before I jump into the product, what are a few reasons we might want to translate MATLAB code into C? First is to actually put it on an embedded system, or to give it to software engineers, or colleagues who are working within a C environment. It's also so you can prototype algorithms and then run them as standalone executables, and to accelerate certain classes of MATLAB algorithms, which is what we're going to be focusing on today. Now, there are a few ways that we can take MATLAB code and turn it into C. We could rewrite it. We could have a software engineer rewriting the MATLAB code in C, but this comes with some challenges. First, we need to now have multiple implementations of both. If we change the requirements, or if we have to change the MATLAB code, then we have to go find where it is in the C code and update that as well. So it makes it difficult to change things afterwards or to debug. It also means you have to have a separate test set so that you can test the MATLAB code and the C code to make sure that they're giving you the same thing. Because you're recoding it, there's a whole new opportunity for manual coding errors, and that's time-consuming and expensive. So we're going to use a product called MATLAB Coder right now to generate C code automatically. So what we're going to do is take the code on the left, which is a simple MATLAB function, about as simple as they come, and auto-generate the code on the right, equivalent C code. And we're going to do this just by pushing a few buttons. So I have my multiply file right here. MATLAB Coder is an app. Apps are interactive user interfaces where you can do some unit of work interactively. So for this example, we'll just go through a quick multiply example. I'm going to add multiply as the entry point function. And then I need to define how it's going to be called. So MATLAB's polymorphic. It doesn't care how you call multiply. I can call multiply with scalars. I can call it with matrices and scalars. I can multiply multiply pi by myself. Doesn't make much sense, but I can do it. MATLAB doesn't care. We can't do that in C. C is a statically typed language, so we need to define how things are going to look. So I have a test suite which calls multiply in a bunch of different ways. Calls it here with random 3x4 and 4x5 matrices, 5x15 and 15x5, and 10x7 and 7x5. Okay, and then I have a test case also to say, well, in this case it's fairly simple, that the result of multiply is equivalent to A times B, but you can obviously envision this being more complicated for a more complicated example. So I'm going to auto-define the types by calling my test suite. It's going to run it. It's going to see everywhere that multiply was called, and then give me the edges or the edge conditions for how to call multiply. So we can see that it says that A is a double precision up to 10 by up to 15. B is a double precision up to 15 by exactly 5. So it's still hardwiring everything it can, because the more things it can hardwire, the more efficient it can be and the smaller footprint it can have. Now we want to actually make sure that our C code is going to give us the same results as our MATLAB code. So I'm going to generate the C code. I'm going to compile it into a MEX file, which stands for MATLAB executable. It's compiled C code with some wrappers around it so that it can communicate with MATLAB. And then we're going to run the MEX file, or we're going to run our test suite, redirecting all those calls to multiply to the multiply MEX file that we just generated. So I'm on a Windows 64-bit system, so we're calling, well, I have this compiled multiply mex.mexw64. We can see that it gave me the same results. So my test passed. And now we can go ahead and generate the source code. So I'll just generate it real quickly first. Right now, MATLAB Coder is going out. It's gathering all the header files it might need. It's building the parse tree, which of course is fairly simple for this function, and then generating the C code. And so now you can see the file we saw at the beginning, multiply.c. You can also see all of the other files that it's included. You can see the MATLAB Coder's hardwiring against worst case scenarios, so it doesn't know if we're going to provide in for NaN values. So if, for example, I knew that I didn't have in for NaN values, I could turn off the support for them in order to speed up this application. And now when I regenerate the C code, we'll see all those header files on the left-hand side have gone away, minimizing the footprint and speeding it up. Okay, so now if you're saying, well, how much faster is multiply going to be than MATLAB's multiply? Well, that's a good question. Before we get to that question, let's just take a look. So with automatic translation of MATLAB to C, you can do your algorithm development within MATLAB. When you need the C code, you can generate it. This allows you to work in MATLAB, do your algorithm development in MATLAB, spend your time improving your algorithms, and then when you need to test your code, you can test both the MATLAB and C versions. So now, we're talking about optimizing our MATLAB code. When will we actually see a speed up with C? Well, it's going to vary. We probably wouldn't see a speed up with my multiply function because MATLAB's already using highly optimized libraries for linear algebra. You will see it for things like signal processing or when you have a for loop with a persistent state that needs to be updated. This is the kind of thing that interpreted languages like MATLAB aren't as good at and that compiled languages can unroll. So let's take a look at an example where the generated C code is much faster. So I'm going to run this example. It's going to play an audio signal. It's going to do a reverberation effect on that signal within MATLAB. And it's going to generate the C code, compile it, and call that compiled C code a couple times.
The discrete Fourier transform.
So right now it's generating the C code. You can do that programmatically too. So now we see we've gone from about a little over 2 seconds to 5 milliseconds. So this is a fairly significant speed up. And the reason we're seeing such a good speed up here is because this is a signal processing application where we have a bunch of states that need to be updated. So we need to loop over this entire audio file and on each iteration update each of the delays and each of the gains. So for loop with a persistent state. So MATLAB Coder doesn't support everything, but it does support a lot of the MATLAB language. It does support about 1,100 MATLAB functions, and we add new ones with each release. So if you have a favorite function that you need C code generation support for, call our tech support and ask them for it. And that's how our development organization decides where to allocate resources. And if you're interested, this has kind of been a small snapshot of a full webinar called MATLAB to C Made Easy that you can watch that goes over MATLAB Coder in a lot more detail. So far, we've been focused on writing more efficient code. Now we're going to switch gears and start looking at using more hardware. So how do I use the additional cores on my laptop, clusters, GPUs? So let's start talking about parallel computing. And what I mean by parallel computing is that I have my MATLAB, toolboxes, Simulink. That's my client. And what I'd like to do is be able to give my MATLAB session access to a bunch of headless MATLAB workers that it can distribute work to. So headless command lines that can run specific commands. So as with anything, there's an ease of use versus control trade-off. With the parallel computing toolbox, we have some things that are very simple to use. It's just a flag that you have to toggle. Use parallel. So I'm going to do an example here where we're going to optimize cell phone tower placement. So I'll run this. And you know how I said earlier that it's the nth run is what you really are timing, because the first run might take a little longer because of the just-in-time compilation. I'm going to run this a second time just to use some of the compilation that happened. Get an accurate timing. You usually want to time the second run. Okay, so we can see didn't take that long, 2.6 seconds, pretty fast. Now let's add more towers. So now I'm optimizing the location of 50 towers. This is a fairly computationally expensive problem. We have 50 towers, each of which has an XY coordinate of the centroid or 100 dimensions. And so what we like to be able to do is to run this in parallel. So it's 23 seconds. In order to run it in parallel, I need to start a parallel pool. So right now this is starting a parallel pool or a par pool using the local profile. So this means the local is the default profile. It comes with the parallel computing toolbox, and it means the hardware available to me on this machine, on this laptop. So it says I'm connected to 2 workers. I have 2 physical cores on my laptop, so I'm opening 2 workers. If you look, you can actually see the processes on my machine. I have a big MATLAB, that's the one with the desktop data documentation, and then I have these 2 smaller ones, which are just headless MATLAB processes. So now I'm going to switch this over to parallel and rerun it. So for this algorithm, that we're using a function from the optimization toolbox called fmincon. It's doing gradient calculations. What it's doing is it's evaluating an objective function at some point, and then perturbing it a little bit in each of, in this case, 100 dimensions to figure out which direction the gradient is the steepest in order to step there. So we can't parallelize the iterations, but we can parallelize those gradient descent calculations where it's looking around in each of those 100 dimensions, because those are all independent processes. So we get in this case a 1.17 times speed up. Whether that's good or not is to be judged. But what I like to think about is how much did it take for me to get that speed up. So fmincon accepts an option structure. Most of them are things related to optimization, tolerances, algorithms. But one of them is this use parallel, and it can be 1 or 0. And if it's 0, then it runs it serially. If it's parallel, it uses those parallel workers that I have. So that's not a whole lot of change that I have to make in order to get a little bit of a speed up. So that's a pretty good return on investment. Now let's drop this back down to 15 towers and rerun it in both parallel and serial. You've probably already noticed that the serial version is faster. So there is communication overhead, having the client MATLAB session communicate with the workers. If the problem's not big enough to make it worth paying this communication overhead, we won't see a speed up. But what's important is that there's typically one elastic point where parallel becomes faster. So serial will be faster until parallel is faster. And as soon as parallel is faster, parallel will remain faster as the problem gets bigger. And you can identify that elastic point using trial and error. It's going to be very problem dependent. We have a lot of products that have this use parallel flag. We've tried to add it to the functions that make sense to have it, so functions that lend themselves well to parallelization and that are typically computationally expensive. So you can search this use parallel flag and it'll show you all the functions available for built-in support like this. Next we have simple programming constructs. So these are going to require a little bit of change to our code, but will allow us to explicitly harness those parallel workers. The first is parfor, or parallel for loop. So the idea behind a parallel for loop is that if the iterations of it are independent, rather than doing one iteration after the other iteration, we'll do those iterations in parallel in time. So I have here the good candidates for this are Monte Carlo simulations, parameter sweeps, or like batch processing of files, where you have to do the same task a lot of times, and each iteration is independent of the others. So what happens when MATLAB sees a parfor loop? It sees the parfor loop. It figures out how many workers it has available. It looks at how many iterations it has to do and does some optimization to try and intelligently chunk those iterations amongst the workers. It does do internal load balancing, and then as the workers free up, they're given new work. So I'm going to do a parameter sweep study of a truss under a dynamic load. So what would happen if somebody jumped onto this as if it was a diving board and dived off? How much would that tip displace? We're going to be sweeping over the cross-sectional area of the members in this truss and the number of elements in the top chord. So to set this up, I'm first going to build a mesh grid of all of the cross-sectional areas and number of elements that I want to use. So if we look at A grid, you'll notice that every row of it is the same. N grid, every column is the same. This is similar to what we were doing earlier. And they're 8 by 8s, so we're going to be doing 64 different combinations. I'm then going to run a for loop over the number of elements in the grid, and on each iteration, solve the truss cantilever problem, and then record the peak displacement at the tip. So this is a fairly computationally expensive finite element simulation that we're doing, and we're running it 64 times right now. So it took almost 11 seconds. If you actually want to see the results of the parameter sweep, we can see the results, and the actual problem we're solving is this dynamic truss simulation. So what I'd like to do is parallelize this. I'm going to take this regular for loop and turn it into a parfor loop and rerun this section. You'll see the bottom left-hand corner of the desktop is green, indicating that my parallel workers are working. And we can see it took just over half the time. So actually, this is a pretty good speed up. It's actually pretty close to being linear with the number of workers that I have. I have 2 workers. It's almost a 2x speed up. It'll never be perfectly linear because there is communication overhead, but it can scale well depending on the problem. Now you might wonder what makes a problem a good candidate for scaling well. Well, let's look at this code. So this entire body of the parfor loop has to be moved to each worker in order to run. It needs to be given hooks into any data that it might need, and a hook back to any data that it has to return. So right now, we need to communicate on each iteration a scalar, a second scalar, and we have to get back from that iteration a scalar, or about 24 bytes of communication overhead. On each iteration, we're solving this big truss cantilever problem where we go in, we build up these big finite element matrices, and then solve them inside of an ODE simulator. So we're doing a lot of work relative to the data communication overhead. Can I just take every loop and turn it into a parfor loop? No, you can't. If I introduce a dependency between iterations, you'll see it become underlined in red. This is the code analyzer, but it's a little bit more angry than it was earlier. It's saying the way I've indexed peak vals causes a dependency between iterations, and this will not run. Of course, a regular for loop would be fine with it. So MATLAB sits on top of the MPI library. If you'd like full parallelization, there are low-level constructs. One is SPMD, same program, multiple data, which allows for full message passing and parallelization. So you can have, hey, I'm worker 1, I'm going to do this unit of work. When I'm done, I'm going to ship it off to worker 2. Worker 2 is going to wait from worker 1, do something else, and broadcast it to all of the workers. You can do that level of parallelization if you need to. There's also parf-eval. Parf-eval allows you to submit a bunch of iterations and then have them run in a first in, first out style queue. This is good for like needle in the haystack type problems where you need to run until some condition is met and then you can stop. Where with parfor that's not an option because we don't know what order things are running in. So now what we'd like to do is take the code that we have running and offload it. And by offload, I mean offload it both locally to this machine that I have available to me right now, to my laptop, and then also offload it to a cluster or cloud environment. So this is going to be a little bit different. I'm going to take my code and any files that I need. I'm going to offload it to a scheduler. Scheduler is controlling a bunch of nodes on a cluster. The scheduler is going to govern how it's distributed amongst the cluster, and then retrieve the work from it. And then we can retrieve that work back into our MATLAB session from the scheduler. So the first way that we're going to do this is using the batch command. And what we're going to do is we're going to offload a serial MATLAB scripter function. So it's going to be offloaded. It's going to run on one worker. That worker is going to do it and give the results back. So I have param sweep serial. Param sweep serial is a serial version of the script, serial functional version of the script we just saw. So it takes in the number of elements in their number of cross-sectional areas, and then runs a for loop, a regular serial for loop over the grid values. Now this is kind of important to point out that there's nothing parallel about this function. It's just a regular function. There could be dependencies in here. We just want to offload the call to this function. So I'm going to offload param sweep serial. I'm going to request 4 outputs. That's how many it had. And I'm going to now do the simulation over a 10 by 10 grid instead of a 8 by 8 grid like we saw earlier. When I ran that, you might have seen this little warning: this job will remain queued until the parallel pool is closed. Batch jobs require their own pool to open with them. So I can't have the pool that I've opened right now because I don't have enough resources available on my laptop. So that's actually why I have this delete GCP no create to silently close that pool, or I can shut it down interactively from the bottom side of the MATLAB desktop. So it'll shut down, and as soon as that shuts down, this job will probably be running. And you might have noticed something in that the job is running, but I can still use my command line. So I've offloaded this function call. It's still running on my laptop, but my command line is free to continue working, so I can keep doing other things. And that's something that's really, really powerful. If you have something that's going to take 10 minutes to run, rather than running it and waiting the 10 minutes before you can continue interacting, use batch to submit it, and then when it's done, we can query it back in. So it's probably finished by now. I could wait for it if I had to, and then we can fetch the outputs from it to get the results back. So that's offloading a serial script. If we have a parallel scripter function, we now want to give our batch job access to a pool of n workers. So that if there's a parfor or SPMD or parf eval inside of that scripter function, it will run on the workers in the pool that the batch job starts on its own. I'm going to change this to run param sweep parallel. Param sweep parallel is the same thing as a serial one, only that loop is a parfor loop. And when I run this, it'll run, and it'll run with a pool of 1. Now you might be wondering, what's the point of having a pool of size 1? Now I'm using a parfor loop, which has additional overhead to a regular for loop, but I'm not going to be seeing any of the benefits that come with having additional workers to work at it. And that's an absolutely correct thought. The point of giving this a pool of 1 isn't to speed it up, it's to prototype. I want to make sure that I can submit my parallel parameter sweep and have it run. I'm not worried about the time. It ran, I can get the results back. The reason I'm prototyping this is because it's a lot easier to debug on my local machine than it is to debug on another machine. So now what we'd like to do is scale this up. So far I've been using just the parallel computing toolbox to parallelize locally. It'll allow me to take advantage of as many local cores as I have. But now I'd like to take advantage of a cluster or cloud environment. So what I'm going to do is use the MATLAB distributed computing server to swap out the hardware that I'm using without changing the algorithm. So MATLAB distributed computing server is a different type of license. It's installed on the cluster or cloud, and it's licensed by number of workers. So it could be 32 workers or 64 workers or 4,000 workers. To take advantage of it, I'm going to go in and I'm going to swap out my default cluster from being my local cluster to being R2015B MDCS32. So this is a cluster that we have at our headquarters that I'm going to tie into to take advantage of. It has access to 32 workers. So now I'm going to submit that same parameter sweep serial job to it. And then I'm going to scale up the parallel parameter sweep to use a pool of size 30. And I'm going to do it for a 50 by 50 grid, so 2,500 simulations instead of 100. Offload it. And now both of those jobs are out there running. At this point, I can actually go ahead and close MATLAB. Okay, those jobs are free. They're free from my desktop. They've been handed off to the scheduler. The scheduler is distributing them on that cluster. Now there's a lot going on to make this happen. That's all happening natively with just this batch command. Let's take a look at this job2 object. First off, we're offloading this to a cluster. In this case, that cluster is actually a Linux cluster. I'm on Windows. Those machines don't have any of the functions or files that I need. So this batch job included the MATLAB functions that were required for this to run. It did a dependency analysis and identified what it needed and shipped them over. If I needed to do operations on large amounts of data, I would probably have the data already living on that cluster, and I would need to add the path to it so that the MATLAB batch job could see the data available. Okay. Even if I was to clear all of this out, I can retrieve the jobs using the interactive job monitor. So we can see that the jobs up here finished, and I can fetch the outputs from them. And when I fetch the outputs, I can then go ahead and visualize them. So if we want to visualize the output for job 8, we can see the output. So that's the big parameter sweep, 50 by 50 grid. So this is how you use the MATLAB distributed computing server to offload a lot of work and to scale up your algorithms. These jobs are actually tying up resources on the cluster. So as a good cluster citizen, I'm going to delete them so that they're no longer tying up those resources. And finally, we have GPUs. So GPUs are graphics processing units, originally for doing graphics calculations, but they're also useful for scientific computing when you have to do lots of simple math. So these have lots of many parallel processors and then dedicated high-speed memory that each of these processors can take advantage of. So it's a completely different architecture. Where my laptop has 2 physical cores, a GPU might have hundreds, but they're not the same type of core, so cores aren't even necessarily a good metric for GPUs. So the MATLAB Parallel Computing Toolbox supports NVIDIA GPUs with, as of R2014B, compute capability 2.0 or greater. You can go to the NVIDIA website to see what GPUs meet this if you're looking to spec out a GPU. Just like earlier, there's built-in toolbox support for GPUs, but the most common way to use them is through the GPU array interface. So we're going to solve the second-order wave equation using spectral methods, and we're going to do it with both a CPU and a GPU. So first I'll run this with a small grid for 4,000 time steps. So this is the equation we're solving. And you can see it's fairly fast for a small grid. But if I make the grid a lot larger, it slows right down. Now I don't have a GPU on my laptop, or well, I do have a GPU, but it's not powerful enough to be supported for this. I have a video of a GPU running this wave equation against a CPU. The left is the GPU, the right is the CPU. And you can see that the GPU is much faster. And if I just fast forward to the end here, we'll see that the GPU ends up being about 10 times faster. So it's able to do 200,000 iterations in about the same time that the CPU does 20,000. So we usually say you can expect an up to 20 times speed up for problems that are well suited for GPUs. But once again, let's look at what makes this a good candidate for a GPU. So on the left we'll have the CPU code, and on the right we'll have the GPU code. In order to actually get this to run on the GPU, I need to say that x equals GPU array of x. This takes the array x and copies it into the GPU memory, holding on to just a reference to x. Y equals x transpose happens on the GPU. There are a few other things that we need to move to the GPU, so we'll turn those into GPU arrays. And then the bulk of the algorithm all runs on the GPU. In order to update that user interface, because these variables live on the GPU, we need to explicitly gather them back in order to bring them back into the client memory. Now, if we're looking at the algorithm here, we can see that it's a lot of simple floating point math operations. Indexing, dot transpose, f of t, real, dot times, minus, IFFT, almost all simple math. So GPUs do really well with this because they can parallelize over it. They don't do as well with branching, so you don't see things if, else, switch case in here. So we also have the advanced programming constructs for GPUs. So you have SPMD. If you want to have multiple GPUs, you can have each worker owning its own GPU. There's a array-fun, allows you to build the CUDA kernel once and reuse it over and over again. So if you see a for loop over GPU array elements, you might want to be thinking about array-fun. And then if you write CUDA, which is a language NVIDIA uses for their GPUs, you can incorporate those PTX files into MATLAB directly. With that, we're going to summarize and then talk about a few additional resources you can use. So the first is to use the native features of the MATLAB language. It's already a fast language. It already has lots of things for performance built right in, so take advantage of them. Spend your time addressing the actual critical areas of your application. And to help with this, you have the MATLAB profiler. For some applications, consider using MATLAB Coder to generate equivalent C code for subsets of your algorithm. And then finally, consider using parallel and distributed tools to take advantage of your local cores, GPUs, and clusters if you have access to them, or clouds. A few other places to look for information in the MATLAB documentation under Advanced Software Development. There's a Performance and Memory section that discusses some things you can do to increase performance and minimize memory consumption. There's a newsletter on accelerating algorithms. Lauren has a blog titled The Art of MATLAB, where lots of this type of discussion goes on. And finally, my favorite, which is MATLAB Answers. It's an online question and answers style forum where you can go ask questions, and people from the community and sometimes from MathWorks will answer them. So if you're stuck, or if you have something that you just need to speed up a little bit, you can post it on there, and hopefully somebody can help you make it a little bit faster.